Okay, so today's sample problem is going to be hopefully something familiar to some of you, which is, let's imagine that we have a hockey puck. And let's say that there are three forces acting on this hockey puck. Let's say that one force is coming in like this way. Let's call this, I don't know, Michael Jordan 23 degrees, and let's give it a force of 30 newtons. Okay, I got to speed up a little bit. I did not get great sleep last night, so my brain is a little bit foggy, but you know what? Let's just kick this into high gear. No more excuses. It's physics time. All right. Let's have another force coming in at some deeper angle right here. Let's call this angle 70 degrees, and let's give this force a little bit of a stronger force. Let's say it's 40 newtons. And then let's maybe even give a third force going this way. And then let's say that this angle here is, let's give it 40 degrees, and let's say that this one is 35 newtons. I lied. Let's make something a little bit different. Let's say that this force right here is 70 newtons. So this is a bit of a stronger force. Okay. And notice that I'm always giving the angles in terms of with respect to the horizontal. That's just usually the way that I like to do it. It doesn't have to be that way. And then let's imagine that the first thing we're interested in here, question A, is what is the net force on the puck and in which direction? All right, so that's going to be what we're trying to get to right here. So let me just get a different color here, green. Okay. So, oh, we also and let's just give a mass of the puck. Let's say mass is 0.26 kilograms for the puck. All right, so mass is 0.26. And let's even give a coefficient of kinetic friction for this puck to be, it's a puck on ice, so you don't want that coefficient to be too high. Let's call it 1.13, or it's 0.13. Okay. So we're trying to figure out the net force on the puck. You can imagine we got these three forces acting on the puck, and all three forces have an x and a y component to them. So we better break it into their x and y components first. Let's go a little Christmassy here. So we're going to do a little red. So we have F1x. I'm just going to call this force 1. Let's call this force 2. Let's call this force 3. Just so you can see where my subscripts are coming from. So F1x goes this way. F1y goes up like that. For 2, F2y goes downward. And again, these directions are super important because they'll tell you the plus or minuses as we start to add all these forces together. And then the F2x goes off to the right as well. The F3y is also going down. And the F3x goes to the left. Ooh, one going to the left. All right. And so here, these are the forces broken into the x and y components. The first thing we got to do is figure out what is the total net force in the x direction. And then we're going to have to, of course, figure out the total net force in the y direction, F net y. And then from that, we can figure out what is the total net force. So we're going to get the x and the y first. So let's do that. Well, the net force in the x direction is going to be the combination of this, and this. Notice how F1 and F2 are both positive forces, and I'm calling positive to the right here, and then F2 or F3 is a negative force. So think of it this way. It's going to be F1x plus F2x minus F3x. Again, that negative comes from the fact that it's going this way. We'll get to the y's in just a moment, so I'm just going to erase that for right now. All right, F1x. F1x is just simply 30 cos 23. F2x is simply 70 cos 40. And F3x is 40 cos 70. Just make sure I got those right. We got a 30, we got a 70, and a 40. Okay. So now it's going to be calculator time. In this case, I will crunch out these numbers. Why? Because I'm just super awesome and feeling generous. And you know what? It's kind of the holiday season, and frankly, you deserve a little bit of a calculation. So it's plus 70 cosine 40 minus 40 cos 70. And I get 90.36. It's positive, which means that, of course, it means it's going this way. All right, let's do the same nonsense on the y direction. Well, in the y direction, let me just switch this to pink, I guess. In the y direction, here we have a positive f1y. We've got a negative f2y. And we've got a negative f3y. So remember, these directions of the forces are critical. So it's going to be a it's going to be a f1 was positive. So f1y minus f2y minus f3y. Again, the f1 is positive, negative, negative. And now let's do the same deal. This is going to be 30 sine 23 minus 70 sine 40 minus 40 sine 70. And notice that all we really did was swap the cosines for the sines. And of course, we got to be careful with our plus and minuses, but that's, you know, it's not too complicated to figure out what these three expressions are. So let's crank this out. 30 sine 23 minus 70. It's a sloppy 70. 70 sine 40 minus 40 sine 70. And I get, making sure I did this, making sure I typed it in right. Yeah, okay. So this is a negative 70.86 newtons, which tells you that the net force in the y direction actually goes downward. So take a look at these vectors here. I didn't have to draw those. You can tell just from the pluses or the minuses, by the way. But I just want to point out that this is how we're going to construct our triangle. So in the y direction, or sorry, in the to figure out the net force, we're going to say that it goes 90.36 this way. I can say newtons if I want. Then it's going to go 70.86 newtons that way. I don't have to put a negative because my vector shows it going downward. And then I'm going to quickly just shift this up here. Okay. And now the net force is going to be this piece right here. And then the theta is, of course, the direction. So we can actually figure out theta right now. Inverse tangent of 70.86 all over 90.36 equals theta. So theta equals, come on, TI-83, don't let me down. 70.86 divided by 90.36, 38.1. All right, so this thing's gonna go off this way at an angle of 38.1 degrees. That's how the net force, or that's the direction of the net force. And we could figure out what is the value of the net force, the magnitude of it, by just doing Pythagorean theorem. Again, I want to stress that I don't need a negative on this 70 because the vector shows it going downward. F net equals, alrighty, 90.36 squared plus 70.86 squared equals, and then I take the square, and then apparently I hit the wrong button. So 90.36 squared plus 70.86 squared, 86 squared, take these square roots, 114.83. Okay, so here are our answers for the first part. The net force is 114.83 newtons. 114.83 newtons. And so there are your answers right there. Okay, we're not done yet. Now let's imagine that I can actually get another slide on here. So what I'm going to do is actually I'm going to erase some of the stuff since it's a video, and let's answer out what the next question is. So I'm going to erase a bunch of this stuff. Leaving our previous answers. So let's say that was that. Okay, let's say part B says, what is the acceleration of the puck? Okay, so we know the direction of the net force, we know the angle of the net force, but what about the actual acceleration of the puck? Well, here, I'm just going to take a side view for a moment. All right, so this is a side view. The puck is sitting on the ice like this, and it's got a push right here. Let me just shift that over to the other side. That there is a net force in this direction of 114.83 newtons. Now, there's a frictional force that opposes this, like that, right? And so the net result of that will be, the puck, of course, will accelerate down this way, but it's not going to be, it's going to be slowed down a little bit because of the frictional force. So F net equals ma. You're going to have the force of the push minus the force of friction equals your ma. This will be 114.83 minus the force of friction is mu sub k times the normal force equals ma. So 114.83 minus 0.13. Now the normal force on a flat surface, remember that this is mg downward and that this is the normal force upward. Since this object is not accelerating up or down, you know that the normal force has to be equal to mg. And since there's no, weird angle like this that you're pushing on this or pulling on it, you don't have to worry about any adjustment to the normal force. So this is just simply going to be mg, which is 0.26 times 9.8. And divide all that stuff by m, which is 0.26, and that will get you a. So in order to save, I think my time's running short if I want to get this posted to YouTube, so I'm just going to stop right there. These are all the numbers you need. Here you can see this is the force of the push minus mu times the normal force divided by m, and that will get you the a of the puck. Any other questions about motion are just simply your motion equations, and now that you have a, you should be good to go.